Hello, welcome to the Electromagnetism Masterclass for Unit 3 Physics. Let me know if you can see the screen, just like react to my latest message. Alright, cool. Oof, that's D for presentation, that's rip. Okay, so this is how tonight's gonna go. Yeah, I am very qualified to be doing this. This is gonna be like the new thing that the 2025 grad mentors are gonna be doing. It's like a module for a specific theory part of the unit, so like not an overall thing for unit 3 or 4. It's gonna be only electromagnetism and electromagnetism only. So yeah, only some relevant sections of unit 4, like one definition, but that's it. I'll be going straight through the content. So if you have any questions, please just hold on to them and we'll get to them very shortly because I'm gonna go through it like a lecture style, and then we'll have questions about electromagnetism, and then we'll do a practice question section, and I'll ping everyone when that is beginning. So what will you be dealing with in... Okay, so you can't hear. Can anyone else hear me? Here, Sean. Yeah. Okay. Casey, maybe just check your Discord speaker sound things. Yeah, I'm speaking, Forge RLO. Yeah, I'm speaking. Okay. Technical difficulties. This happened last year, I remember. I think the solution was just to like rejoin and hope it works, or like restart Discord. If that doesn't work, then I'm like not sure. Okay, I'll tell in chat. Alright, I'll continue on though. So, the formulas for electromagnetism are some formulas you're gonna really get to know and love. Yeah, Sean, this is being recorded. I'm recording it. Yep. Yeah, so you're really gonna get to know these formulas intimately, each and every one of them. Maybe not like to the same degree, like they'll definitely be favorites, but you're gonna get to know each and every one of them eventually, and you'll have to use them in like some pretty cooked questions. So, yep, intimately, yep. So all the formulas except one or two are gonna be on the formula sheet. You're gonna be using them. You should get to know them a lot. People still can't hear. Okay. Were you able to hear the music in the stage channel before I started speaking? Okay. Just check your Discord settings and like see what speaker it's like playing out of. If you need me to go over anything, like really burning questions, just ask. Oh wait, they can't hear. Okay. For the sake of like time and like the recording, I'm gonna continue on, but just just keep trying it. Like you're not missing too much right now. Okay. So Coulomb's law, for those of you who can hear the audio, Coulomb's law is a law about force and charge. So all the letters mean is force is Newton's. We all know what force is. At least I hope you do. So Q and small q, big Q and small q, are the strength of the electric charge of a particle or a point. They are different. So big Q is one point, little q is another. It really doesn't matter which one you say which is which, just be consistent. R is the distance between the center of the electric points, and this is in meters. The big 1/4 pi thingy, that is just a constant. It's on the formula sheet. You don't need to really know what that is. Important things to know are units, especially if it says like millicoulombs, millimeters, kilometers, all that stuff. Don't forget R squared. This is a big like tripper. And this is like the sort of definition of the equation. Just like, charge, repel, opposite attract. Stronger, closer, weaker, further away. The formal definition is that like the attractive force between opposite charges is proportional to the product of the charges, and it's inversely proportional to the square of the distance. And yep. Repulsive. The force is repulsive when the charges are the same. So if they're negative, positive, they're opposite, so they attract. If it's positive, positive, or negative, negative, then they're the same and they repel. Like you can sort of work that out with the Coulomb's law by calculating F, and if F is negative, that means that it's positive negative for the charges, so it's an attractive force. And if F is positive, then it's either positive positive or negative negative when you multiply the charges, resulting in a positive force. So it's gonna be repulsive. Electrical field strength is directly related to Coulomb's law. This is a concept that about electric fields, and it's related to their strength at a particular point. So basically, how strong is an electric field at this point? If you put a charged particle, how much force will it exert on that particle? So E is the electric field strength, and that's what the whole formula is about. And this is newtons per coulomb, because it's equal to F over Q. F is newtons, Q is coulombs. F is the force that we calculated just a previous slide from Coulomb's law. Q is the charge of the particle in the field. And you will often have to find Coulomb's law first before finding E. Or you could just, if you have all the variables like the distance and your charge in the electric field, then you could calculate it from there, because you can see that the formula only uses one Q, not two Qs. It uses only one charge because we're not talking about the relationship between two charges. We're talking about the force on a single charge in an electric field. So definition, strength of an electric field at a certain point is the force on a unit charge, or in other words, the force per coulomb at a certain point. Now, a side note about electric fields is, this is very important when talking about like motion of particles and like how they interact with particles. So positive charges will accelerate in the direction of the electric field lines. Negative charges accelerate in the opposite direction of the field lines. The field lines in an electric field, for example, up in here, if you have field lines going this way, then that means a positive charge will go in the same direction. That's what the electric field lines represent. And a negative charge will go in the opposite direction. With charged particles, which I'll abbreviate to CP, in electric fields, CP can accelerate from a standstill because the charge in the particle is interacting with the electric fields, the electric field is interacting with a charge in the particle based on the formula of E equals F over Q. So the charge of the particle, charge of CP, will generate a force on CP which can accelerate it. Since force is mass times acceleration, it can accelerate it from a standstill. Only in an electric field though. And you can remember this by remembering A. The sound of A in accelerate sounds similar to electric field. Accelerate, electric field, right? But in magnetic fields, they must be moving. And you can tie this with the words both starting with the letter M. So CP must be moving to accelerate in magnetic fields with M and M. Okay, this formula is possibly the nichest formula on the formula sheet by far. And I'm gonna run you through on what it actually means and how to use it and to unlock a secret formula that's not on the formula sheet. So this is voltage, and it's relating voltage to delta U, which is energy or change in energy or work. So V is voltage in volts, delta U is change in energy in joules. And it must be the final energy minus the initial energy. So the energy you started with and the energy you ended up with. The Q is the charge of CP in the electric field. And the meaning of this formula is that the voltage across 2 points is equal to the change in energy of a charged particle if it was put at the start of 1 point. So normally this is related with electric plates. So you would have, say, this is 5 volts, and you would have a particle at the start, and the electric field lines are going down. So what this formula is saying is that the energy between charged particle 1 and charged particle 2, the change in energy is equal to VQ, or the voltage is equal to the change in energy per coulomb. And this is only really used in one one scenario and one use case. It's really only used to calculate velocity of a charged particle after being accelerated through an electric field, because the work change in energy is in joules, kinetic energy is also in joules, and you can use kinetic energy to find the velocity of the charged particle. So this is not on the formula sheet, but it can be unlocked with the previous formula we used. This is niche ball knowledge, so listen up to whoever can here. We are using V equals ED. This means the voltage is equal to electric field strength between to the 2 points times the displacement between the 2 points. This is almost always exclusive to parallel electric plates, or where there's a uniform electric field, which is almost parallel electric plates. The voltage of the particular point in that field is the electric field times the displacement. So voltage is proportional to electric field strength and displacement from origin of electric field. And this is how we derive the formula. So we start with the electric field strength. So we have F, the force is equal to E times Q. From the formula sheet, we have work equals force times displacement. So work equals force, which is EQ. So work equals EQ times displacement, which also equals delta U. Delta U, as we know, is equal to VQ if we rearrange V equals delta U over Q. EQS equals VQ because we had EQS equals delta U and delta U equals VQ. Therefore, we know that voltage is equal to ES or ED, S slash D being displacement. And we get here by cancelling the Q's. And this W is work, and it's also delta U, the same as delta U. So what does this mean for voltage? The true definition of voltage based on all of these formulas is that voltage is a measure of energy, delta U, that's required to move a unit charge a certain distance in an electric field. So if you had an electric field, the voltage is the energy required to move a charge a certain distance. That energy is the voltage. Does anyone need me to go go over that? Yeah, for those that can hear. Okay, these are the rules that will save your life in the electromagnetism exams. You need to know these rules. You need to know them like the back of your hand. These are the right hand grip and slap rules. The right hand grip rule is used to find direction of magnetic field or current flow. To get this rule, you'll get to hold out your right hand, and you hold it out in a loose thumbs up shape. So do a thumbs up, but then relax your fingers a bit so that they hang out from the palm of your hand a bit. It's like if you're holding a water bottle, a TV remote, or other cylindrical objects. So what this looks like is your thumb and your fingers in the hands. So your thumb points right up and your fingers curl around. The thumb is the direction of either current or magnetic field. The curl of your fingers is the direction of the magnetic field to the current, or the direction of current to the magnetic field. The meaning can be used interchangeably. You don't need to have your thumb be specifically one variable. You just need it to be consistent. So if your thumb's the current, then your fingers curl is the other component. If your thumb's the current, your fingers curl is the magnetic field. If your thumb's the magnetic field, your fingers curl is the direction of current. It doesn't have to be restricted to current or magnetic field. It can be used interchangeably as long as your finger or thumb is the other one. The right hand slap rule is used to find direction of force. So, direction of force for a moving current or moving charged particle. To get the right hand slap rule, you hold your right hand flat and you have your thumb go at a right angle to your fingers. What this represents is your palm is the force that the current carrying wire or the moving charged particle represents. Your fingers are the magnetic field direction that the current carrying wire is in or the charged particle is moving in. And the thumb is the current flow or the movement of a charged particle in the magnetic field. One thing to note is that negative charge flips the direction. So you either look at the direction of the back of your hand or you use your left hand's palm. Now, the magnetic field of a wire, this is where the right hand grip rule plays into. B is the magnetic field strength, so it's Tesla's T. The mu naught, the weird looking U, is a constant. I is the current of the wire. R is the distance of measurement from the center of the wire. And 2 pi is 2 pi. So what this is saying is that magnetic field strength is proportional to current. So the higher your current is in your wire, the stronger your magnetic field is. But the further away you are from the wire, the weaker the magnetic field is. The direction of the magnetic field from the current carrying wire is given by the right hand grip rule. For a solenoid, you still use the right hand grip rule, but instead of your thumb being current, your thumb is the magnetic field direction, and your fingers curl is the flow of current. A solenoid is essentially just a bunch of coiled wires. It's something along the lines of this. But the coils will be spaced much closer. So same thing, B is B is magnetic field strength. The mu naught is constant, and it's the same constant from the previous equation. I is the current of the solenoid. N, however, is the number of loops per meter. And this is equal to big N over L. And this is number of loops per the meters that the solenoid measures, how long the solenoid is. So magnetic field strength is proportional to the number of coils per meter in a solenoid and proportional to the current of the solenoid. And the direction of the flow of current around the solenoid is given by right-hand grip rule. So if the magnetic field were to be going this way, if you use the right-hand grip rule, the flow of current will be curling from the bottom side up. So the flow of current will be curling this way if you use the right-hand grip rule. This is the right-hand slap rule now. The force on a current-carrying wire in a magnetic field. It's force newtons. Magnetic field strength, current, length of wire. This is important. And the angle of the wire from the magnetic field lines. So if you had a magnetic field and you had a wire, the angle would be of the wire from the magnetic field lines. Then the direction of force is given by the right-hand slap rule. So if your current was going that way in the wire, then your... Wait, can I turn on subtitles? Okay, wait, can everyone see the subtitles? So, okay, it's not doing anything. Okay, so if your current was going this way in the current carrying wire in the magnetic field, then your force from the right-hand slap rule will be in the direction into the page. So now the force on a moving charged particle is the exact same thing. It's just you replace the wire with the moving particle, the particle's charge and its velocity. So you replace the current times the length by the charge times the velocity. So force is Newton's, Q is charge of Cp, and remember a negative charge particle flips the direction of force. The velocity is v, and b is magnetic field, and angle is the angle from the magnetic field lines. And the direction of force is given by the right-hand slap rule. Now magnetic flux is very simple. It's just the amount of area in a magnetic field and how strong the magnetic field is. So essentially the density of the magnetic field lines in an area. So if you had magnetic field lines and you had a square, that would be the flux, the amount of magnetic field lines in that area. So flux is proportional to both magnetic field and area in the magnetic field, and theta is the angle of the perpendicular of the flat area. So this is the perpendicular. Theta is the angle from there. So if we had something like this, then theta would be the angle measured from the perpendicular. So not the actual orientation of the plane itself, not the area itself, but the perpendicular of the area. So you can find that by finding the angle between the area and the wires and subtracting that from 90 degrees. Now, induction or Faraday's law. This is one of the highest yield topics in the exam, or not the highest yield, but definitely the most cooked questions come from this topic in terms of electromagnetism, and is the topic that all students struggle with most. So what is it? EMF is electromotive force. It's in voltage. It's in volts. N is the number of coils in the circuit, and you'll notice this is big N, not little n. Theta is magnetic flux. The B, A, those are from the magnetic flux, so they're the same meaning as the magnetic flux formula. T is the time taken for the change in flux in seconds. And the little triangle stands for delta, and it stands for the change in quantity. Now, the equations related to transformers. I is the current of the circuit and solenoid. The V is the voltage. Big N is the number of coils. You'll notice it's big N, not little n. P and S in the subscript denote the primary or secondary transformer. And one thing to note is if a transformer decreases voltage from P to S, it's a step down transformer, and if it increases, it is a step up transformer. Before I go into the concepts, let me just check my Discord. Okay, can people hear me now? Mic test. Can anyone hear me now? Can anyone hear me now? Okay, it seems like there's still the issue. What about now? Okay. Okay, it just seems like it's not working. Why is the... Okay. Yeah, okay, I'm just gonna keep going on. Now, I'm gonna go through the concepts, and these are very, very complicated concepts, very high yield questions, and they tie in very closely to the working you need to do for each question with the electromagnetism formulas. So electric and magnetic fields, as we've explained before, the right hand grip rule, the magnetic fields will always rotate around an electric field, and you can find out the direction using the right hand grip rule. Electric fields can accelerate a charged particle from a standstill. So a charged particle can just be accelerated by an electric field. But for magnetic fields, the charged particle needs to be moving for it to have a force acted upon it. These are defined by field lines and diagrams. So you'll see them drawn, and they'll be noted by stuff like these or these or these. So the dots represent things going out of page, and the crosses are the field going into the page. Now, one thing with these field lines is they represent the force or the movement of a positive charge particle. Negative charge particles will go the opposite way. Electrical potential energy. This is a form of energy from a charged particle's position in an electric field. There's different types of work done depending on what direction the charged particle takes relative to the electric field. Work done on a field is when a charged particle moves against it, and this is positive work. Work done by a field occurs when a charged particle moves as it would normally do. And you can think of this as a natural release of built up energy by the electric field. So it's negative work, as nothing is required for it to happen. It's just a natural phenomenon of nature. And you can think of work done on a field and remember it because the charged particle needs to have something exerting a force on it to move against a field. And that work, the recipient of that work would be the electric field, because you need to be pushing actively against what it would naturally go. So to illustrate this, if a particle were to go against, that would be positive work on the field. And then if a particle were to go with the field, it's negative work. It's just a natural release of the built up energy. And that is done by the field. Okay, light. This is the definition of light. This is technically Unit 4 content, but it's so closely related to electromagnetism that I've included it here. And it's a relatively small definition, so it's really easy to get through. So the key things you need to mention for a definition of light is that it's an electromagnetic wave. And for a photon, like a particle of light specifically, you need to say that it's an electromagnetic wave that's mutually oscillating. So when one goes up, the other goes down. It's perpendicular, so the waves are at right angles to each other. So I'll draw a better picture. The waves in particular are electric and magnetic fields. The change in a magnetic field induces a change in an electric field, and we'll cover that later. And this is why it is self-propagating. So the induction from a magnetic field to change in an electric field implies and causes the self-propagating nature of light. So that is why it can travel in a vacuum, and you need to mention that it travels at the speed of light, c, in a vacuum. Okay, induction. This is essentially Faraday's law, which is the EMF formula that we covered earlier. Faraday's law, in plain words, is that the changing magnetic flux will induce a voltage in an electric circuit proportional to the number of coils in the circuit and the magnitude of change in flux. So essentially, like a solenoid, the more coils it has, the bigger the voltage induced in the coil will be. And the bigger the change in flux, the bigger the induced voltage. This is also closely related to transformers, as this is how transformers work. Alternating current in one circuit. So they have, to draw a quick diagram, we have one circuit. So let's call that P. That's the primary circuit. Then we have another circuit, which we'll call S as the secondary circuit. The change in P so we are changing P from bigger to small or small to bigger. In the flux of P will cause a voltage to be induced in S. So S will have a magnetic field going through it, because solenoids, the magnetic field of solenoid wraps radially around it. So magnetic field goes up and into the solenoid, but it also goes and wraps around it in sort of layers like an onion. And the magnetic field that goes into the second circuit causes a magnetic flux. And that changing flux in the circuit of S will cause a voltage to be induced in the circuit of S, and thus a current to be flowing. And that's how transformers work, to increase voltage or decrease voltage to transport it over long distances. Motors and generators, which is out of syllabus for Queensland, but it's really crucial to better understand and relate these topics to everyday life, is that these are essentially the force on a current carrying wire and induction. So motors are just a coil of electrical wire in an electric field, a magnetic field, and when a current is passed through the wire, there is a force generated which rotates the motor, and that creates an acceleration. When the same setup is used, but instead of a current being flown through the wire is actually turning because of mechanical energy by a wind turbine or a dam. It's turning, and because it's turning in a magnetic field, that is a change in flux for that wire. And the change in flux will generate a voltage, will induce a voltage, and that induced voltage will generate a current, which is electricity. And that's how electricity generation works, by wind, by water, by coal plants and nuclear plants. They generate steam to turn the turbines. The spinning coil in a magnetic field, because it is spinning, the area in the magnetic field is changing, so the angle of the area is changing. And if you remember that the formula for magnetic flux is phi equals BA cos theta, because the angle is changing, the magnetic flux is changing, which means there is voltage, and therefore current produced in the coil, and that generates electricity. Motors and generators look like this. And for a motor, there'll be magnetic fields going this way. And let's say there's a current. So there's a current going this way. So current is going through the coil like that. because of the right-hand slap rule, which we use to find the direction of force on a carrying wire in a magnetic field, we use the right-hand slap rule, and we find that due to the right-hand slap rule, there is a force going down here and a force going up here. So because there is a force, the coil will eventually turn, and that's how the motor generates movement from simple electrical force. It's not a moving part, it just uses the relationship and interaction between magnetic fields and current carrying wires. Now, Lenz's law, this is related to induction, and it talks about the direction of a magnetic flux induced from an original magnetic flux. So we've talked about what happens when a magnetic flux changes and what happens to the coil. There's a voltage produced in the coil, but this is actually talking about what direction the voltage induced will act. So what direction does the current flow, and what direction does the magnetic field produced by the coil come out at? So this is essentially a Nutter law. It always opposes original flux. Whichever direction the increase in original flux is, the new flux produced by the coil is opposes it, right? So induced flux, let's say that IDF always opposes the original flux. And the way we can wrap our heads around this is to use our right hand grip rules to figure out A, the direction of the original flux, where it's increasing, and B, what direction the coil will have current flowing or the magnetic field will flow to oppose it. Now, this is a Q&A section, so if you have any burning questions about any of these that I might not have answered while explaining, or you need reclarification of anything, this is your chance to let me know. The red arrows before. Okay, good. Which here? Red arrows are just magnetic field. Oh shit. These should be the other way around. So yeah, so they're the other way around. So that means the force is the other way around. So I'll just say that's B. And that means the force is the other way around. So with the right hand slap rule, we get that the force acts in these directions, and thus there'll be that direction of movement in the motor. That B is in vector notation. It's just a notation to like say it's a magnetic field, like B for magnetic strength, and the notation for the tilde under it is notation that it is a field that is acting. It's in like 3-dimensional space, and it's a bunch of red arrows. So I'm not too sure on the specifics, but I imagine it comes from vector notation, because the magnetic field is really just a bunch of vectors, and they're all just going this way, or in more complicated examples, then they're going turning and all that. Would we have to do vector calculation stuff? Technically you do, but it's included in the formulas. Like if we go back to the formula for the, if you go back to magnetic flux, BA cos theta, that's just the dot product, isn't it? And the force is I'm pretty sure it's related to the cross product. That's why there's the sine theta. And that's why it has to be at right angles to have the maximum force. Oh, and the because it's related to the cross product, that's why the like sort of directions are so weird. That's why it's got like such weird directions. Because you've got your magnetic fields, you've got your currents, and then you've got your force perpendicular. They're all perpendicular, like the cross product, the normal of the cross product of two vectors. Did everyone understand the part about the Faraday's law and the flux? All right. Does anyone have any more questions? Alright, if I'll start the practice questions, so I'll ping everyone. So let's go through some of these practice questions. So these wires are current carrying wires, and we want to know if they attract or repel each other. Does anyone have any answers? Any ideas? Attract? Alright, let's do the working. We've got most people saying attract. So let's see. So the blue wire is, so they have electric fields or currents going that way. So their currents, and because the current is going down, we know that we use right hand grip rule. So down, and it's curling it's curling in this direction. So it's going into the page here. And it's going out of the page here. So that means on this wire, they are going out of the page. Now for the red wire, we use the right hand grip rule, and we see that the magnetic field is curling that way. So it's going into the page here, and then out of the page here. So it's out of the page on the blue wire, and the blue wire is out of the page on the red wire. Now we use right hand slap rule. So we use right hand grip rule to find direction of magnetic field. Now we use the right hand slap rule to find the force on each wire. So with the right hand slap rule on the red wire, we have our things going, so we have the magnetic field going out of the page, but we have the current going up. So take your right hand and point it towards you. So we have right hand. And that's the palm. It's a very bad palm drawing, but that will be the force, because that's the current. That's the magnetic field. Sorry, wrong color. So that's the magnetic field, and that's the force. So the force on the red wire is going away from the blue wire. And the same thing with the blue wire. Because if you just flip your right hand from that position, it's going away. The fuck? Away. So because they're both going away, they attract. They repel. So flatus was the correct one initially. Now, do these wires attract or repel? Surely this one's much easier now that we know the working out behind it. Yeah, they attract. So I'll just quickly do the working out. So we have our magnetic field going that way. So it's into the page and then out of the page. So out of the page on the red wire. Then the red wire is also doing the same thing. So it's out of the page and then into the page on the blue wire. Now we use our right hand slap rule. So right hand grip rule. And right hand slap rule for direction of force. Now, right hand slap rule. So we have current going downwards, magnetic field going out of the page. Using right hand slap rule, we have force going to the blue wire, or the red wire going to the blue wire. Now, we have current going down, but magnetic field going into the page. So that means force going to the red wire for the blue wire. So they attract. Any questions on that? You don't get how to use the hand rules? The right hand grip is for the direction of current and the magnetic field. So with the red wire, you point your thumb down because your thumb represents the current. So why are they the same wire but the direction of the force different though? Because the direction of the force is related to the direction of the current, but also the direction of the magnetic field acting on them. Because the red wire has a magnetic field that is going into the page, if you use the right hand grip rule, so if you use right hand grip rule, your thumb points down, and then your fingers curl into the page. So you have magnetic field going into the page and then out of the page on the other side. And this is the same for the blue wire and the red wire. So because the blue wire has right hand, it has magnetic field going into the page for the blue wire. When you use the right hand slap rule, you point your thumb down and then you have your fingers going down into the page, so that's magnetic field. So you'll have a force going to the right. Does that make sense for everyone? When your right thumb's pointed down, fingers curl clockwise. Is that in or out of the page? Yeah, force is palm facing. And when your right thumb is pointed down, your fingers curl clockwise. So your fingers show the direction of the magnetic field. And you just have to... It's not in or out of the page specifically, but it's a... You have to sort of like see how the page interacts with it. Like it's clockwise around the wire. Like, so just imagine that. What the? Okay. Okay, so just imagine that you have your thumb going down, right? And the magnetic field around it is clockwise. Because it's clockwise, when you view it from like a 2D perspective, and you think of, say your palm is the page. When your fingers curl clockwise, sorry, the back of your hand is the page. When your fingers curl clockwise, your fingers curl away from the back of your hand. So the front of the page is facing you, but it's curling away from the front of the page, so it's going into the page. And then when they curl back on the other end, they're coming back towards the back of your hand, towards you, so they're coming out of the page. Does that answer your question, Han? Yeah, just like if another way to think of it is is the direction your fingers are pointing when they go if they're away from you or if they're to you. If they're away from you, they're into the page. If they're towards you, they're out of the page. So now do you get the difference in magnetic field directions for the different wires? Yeah, so because the magnetic fields have the wires have different magnetic field directions, there will be a difference in force, because we use the right hand swipe rule for force, and because since they're both pointing down, you would expect them to have the same direction of force. But because one of them has a magnetic field out of the page and one of them has a magnetic field into the page, the one into the page, which is the blue wire has a magnetic field into the page noted by the red X. Because of that, the blue wire will have your palm facing to the right. So take your right hand, reach out in front of you like a handshake, and then just flip it 180 degrees. You'll see that your thumb is pointed down and your fingers are pointed away from you. So the magnetic field is into the page. Now, what direction is your palm facing relative to you? Yeah, so the force will go right. Now, for the red wire has a magnetic field going out of the page. So, this is a tricky maneuver to do, but take your handshake position you were just in, and then just sort of flip it, like rotate it towards you, like using your elbow. You should have your fingers pointing like straight at your face, like just in front of your face. You should have your fingers touching your face and your thumb going down, and your elbow will be bent. What direction is your palm pointing now? Left, yeah. So the force will be left, and because we have the blue wire having a force to the right, which is towards the red wire, and the red wire has a force to the left, which is towards the blue wire, they will be attracted. And the same thing for the other question where there were different currents. Do the same thing with that. Like could I explain how the right hand grip rule explains the direction of the magnetic field? That is beyond syllabus. That is way beyond syllabus. Like if you go to the right at the start of the PowerPoint. Is it still showing? Okay. If you go right at the start of the PowerPoint, these equations explain why. Okay. Why is it out and into the page? Like sorry, could you give an example? Do you mean for these questions? Yeah. And the finger curl represents the direction of the magnetic field around the wire. So when you have a current going through a wire or a moving electric charge, then you will have magnetic field rotating around it. And for Servant of King Aura, like for one of the wires, the magnetic field was into the page. Like what? Could you explain, like, pinpoint what you're confused at specifically with that? Oh, the curled fingers, they show the direction of the magnetic field because it's the magnetic field is rotating around a straight current carrying wire. It's the current carrying wire is straight, so the magnetic field is rotating around it. That's just how the physics works. And we went like, hey, this physics is like really confusing with the directions. But we noticed that our right hand is exactly the right like sort of symmetries and orientations to match the direction of current and magnetic fields and their relationship with each other. It's if you like want like a concrete answer to why it does that, then there's like really no way to understand it without like delving into like really complicated math and physics. But the short answer is that the right hand just happens to match the complicated directions the physics takes. Yeah, does that answer your question? Okay, cool. Does anyone have any more questions with the wire stuff? Okay, I'll move on to the next few questions. Alright. So we have some more wire questions. So there's a red wire and a blue wire, and they're just floating in space. Like they're just imagine that they have current going through them, and like they're just stationed there. What is the motion of the red wire? What is the motion of the blue wire? And credit to Flatus for this question. He DM'd it to me the other day. Oh, Han. The motion just like what direction of the force? Like, what's the direction of force on the wires? Like, if we hit play on this sort of simulation, what, where would the red wire go? Where would the blue wire go? Which one is magnetic field direction? They're both wires, so there's both wires. You have to figure out the magnetic field direction yourself. Red, right, blue, up. Yeah, that's partly correct. I'll give yellow. I'll give you a hint. The blue wire is like it's very literal. It's drawing. It ends where it ends and it starts where it starts and it ends where it ends. No. You're right about the blue. Yes. The red doesn't move because there's no magnetic field on the red. Nice job. So the blue wire, it ends here. It ends there, and since the wire is just the magnetic field around the wire literally is just it just exists around the wire. It doesn't exist below the wire, below where it ends. It just exists around the point of the wire. So from the right hand grip rule, we see that it's going out of the page and then into the page. So we've got this kind of direction thing going on, but it literally just ends right here. There's nothing here. Like, no, there's nothing. So there's nothing on the red wire, and because there's nothing on the red wire, there's no force it could have. At least there's no magnetic force it could have. And with the red wire, we have it going into the page. So we have the blue wire, it has magnetic field going into the page at various strengths across its whole like length. So using right hand slap rule, we will have our thumb going to the right, our fingers pointing away from us. And now where does our palm go? Like what direction is our palm facing? No, for the blue wire. What direction is the palm facing? Is our palm facing when we do right hand slap rule on the blue wire? Up, yeah. So you're right about the direction of the force the blue wire has. It goes up. Now, keep in mind the force won't be like consistent because like it's stronger at the base of the wire because it's closer to the red wire. But that's like beyond the point. Like beyond our what we need to know. So, what like all we need to know is that the force, like in general, it goes up. So does anyone have any questions about that? Okay, I'm gonna move on to the next question. Okay, so now this is like the same thing with the last question, except the blue wire is actually like next to the red wire, like it's under the red wire. So what we want to find is essentially the initial motion of the red wire. Like when we hit play, where would the red wire go? Would it go up? Would it go down? Would it go left, right? Where would it go a combination? Hmm. Okay. Okay. Uh, think about the right hand grip rule and like where the direction of the magnetic field curling around the blue wire, and think about the direction of the red wire. Like where's the current going? Out of page and down slightly. Uh, for the magnetic field or for the red wire? Red motion. Okay, okay. You're not. You're not. No one's been right so far. Really, like I'll give you a hint. Like really consider the curl of the magnetic field. Arctic Wolf slap rule is for when you have wire and you know direction of wire, you know direction of magnetic field. Grip rule is for when you don't know one or the other, and you know one, you're trying to find the other. So grip rule has to do with the fields, like the direction of the fields only, while slap rule is the direction of the force. Wait. Okay, I'll give everyone another perspective. So this is the blue wire, so we're looking straight at the blue wire. And this is the red wire on top of it. Now, so the blue wire, how do you know whether to find magnetic field on left or right of blue wire? Well, look at the only thing that matters is where the red wire is in the magnetic field. Like if it was only on the left of the blue wire, you would find magnetic field to the left of the blue wire. But if the red wire is only to the right, you would find magnetic field to the right. Okay, I'll give you're on the right track of thinking with that yellow. Okay. So the red wire is on both the left and right of the blue wire. The red wire it exists to the left and right of the blue wire, so it's gonna be in quite a bit of the blue wire's magnetic field. Okay, I'll give another hint. So with the right hand grip rule, to find the direction of the blue wire's magnetic field, we know that the blue wire will have a magnetic field like this, right? And the blue wire and red wire are like perpendicular to each other, right? They're at right angles. So they will be. So I'll draw another ring out here. So what can you notice about the magnetic field and the red wire and the magnetic field on either side of the blue wire? Going down, not quite. We have the magnetic field going down on the red wire at one point, but that's not true for all of the points. Red moves towards us initially. In which diagram? Original? Okay. Not quite. Okay, so there's not one direction the magnetic field is at across the entirety of the red wire. There's a bunch of directions because it's constantly curling around, like the red wire is in the middle of its curl, basically. So because there's no constant direction of magnetic field on the red wire, what does that mean about the force? Not quite, not quite. There is force on the red wire, at least like with right hand slap rule. So there is force. Oil
or butter.
Yeah, butter. There's butter.
Other than the canola oil,
I don't know.
because it's empty, and I had like six like I wanted 6 cubes of butter, but
Okay.
so I'm using that.
Oh. Okay.
There's just one butter and like little bit of oil. So do you have anything else other than
I don't know. There was butter in the fridge, but someone might have used it then.
well,
Towards blue. No, not quite, not quite. Also, why do I never start stage? Do I? What? Johan, what do you mean? I can't. Oh my god, no one can hear. Okay. Okay, so I'll give the answer. So the red wire is literally like right above the blue wire, and it's in the same plane as the blue wire's curl. Yes, yes, yes. So because there's gonna be force, the magnetic field is going up here. So magnetic field in general, it's going up here. In general, it's going down here. So for the general portion of the red wire, so here there's a magnetic field going down into the page, going up out of the page. Now with right hand slap rule, so we'll have our thumb going towards us. We'll have our fingers. So for the bottom half of the red wire in the original diagram, we'll have our fingers pointing down. So our palm is facing to the right. Oh, that's an ugly green. And the opposite for the other half. Yeah. So it was spin anti-clockwise. And that's just the initial motion though, cuz like once it starts spinning, cuz like the red wire and blue wire are going to like interact with each other cuz their magnetic fields are like literally right on top. So but that's like way too complicated for us to deal with. So but like just as like a thought experiment, it's good to like wrap your head around like the magnetic field and the wire stuff. So does anyone have any questions about that? No? Okay. Moving on. Okay, you're gonna have to use your calculator for this one and actually do some working. Sorry about that. But we can't really do like right hand rules and wires. So let's do some working. So does anyone know where to start with this? CP stands for charged particle. Yeah, Johan, because you're new to the stream, it's just slang. In case you're new to the stream, CP is slang for charged particle. Beansmith, what's this used for? What do you mean for? It's for revising. We're doing a masterclass to like sort of learn electromagnetism and also like revise it a bit, we're on the practice question part of it. Yes, that wasn't a calculus short for calculator reference. Uh, yeah, Han, you're right. We use the formula for V, but like, I'm not gonna tell you. It's like, it's on your formula sheet, so you can just look it up. But you should. It's probably a bit unrealistic to expect everyone to remember it, but because like physics will always have a formula sheet that you can look up. So yeah, you're right with where we start. So V equals delta U over Q. But then what do we do from there? So we know V, we know Q. Yep. Yeah, we'll have change in kinetic energy. So we'll so you notice that it's already has a speed when it enters the plates. So it has a speed of 2 kilometers per hour. So it already has a kinetic energy. Do we plan on doing a titrations masterclass? I'm not sure. Uh, I I'll leave that up to someone else. Like maybe Panda can do it. Panda or Johan. Do you want us to do like a live titration? Hell no, hell no, hell no. Oh, Flatus, you just want a Chem Unit 3 masterclass? Yeah, yeah. Okay, does anyone have an answer for this question? Capital V is voltage. Velocity is always small v. Arctic Wolf, do you want me to go through anything else? Like re go through anything? Actually, no. Sorry, I'll do that. I'll do that after the questions are over. Like, just for the sake of the recording. Okay, does anyone want me to go through the 0.58 meters per second? Okay. Let's check then. So we have V equals delta U over Q, and delta U equals its final minus initial. And so let's first find the direction of the electric field. So we have the electric field going to the left because it's positive here and negative there. And remember, electric field always flows from positive to negative. So the charged particle will actually leave will actually get slowed down by the electric field because it's accelerating it against itself. So we'll have VQ equals delta U, and we know delta U equals unit final minus initial, so let's find the initial. And we know it's kinetic energy, so it's half mv squared. So we know half mass is 1 milligram, which is 1 times 10 to the negative 3 v squared, so 2 times 3.6, because the conversion from kilometers per hour to meters per second. Oh hey Flatus, nice of you to finally hear me. And just do it in the calculator. So times so we have 0.02592 for the initial energy. So we have 5. We'll have negative 5 times 3 equals final minus 0.02592. So the final is equal to negative 14.97. So the particle actually doesn't make it past the second electric plate, but if it were to do it, so consider it does. Consider electric plates. The signs were swapped. So just move this. Okay, I can't move it. Okay. So the charged particle doesn't make it. But let's consider if it did make it and it accelerated it. So we will have 5 times 3 equals final minus. So we will have the final being 15.02592, and that will be half mv squared, and that is equal to that. So to find v, we have v equals 2 times 15, 2 over 1 times 10 to the negative 3, square rooted, and that is equal to 173.35 meters per second. I'm pretty sure the working is right. Whoops, I used the coulombs instead of. Okay, cool. Yeah. The way the original question was designed though, because the electric field was going against the positive charged particle, it actually decelerated it because the electric field accelerates in the direction of the charged particle. So that's on me for making like a not physically possible question, but considering if it was possible, then it would have been 173.35. But does everyone understand that bit about the electric field direction and the whether it accelerates or decelerates the charged particle? Cool. Okay, I'm gonna move on to. Okay, wait, sorry. Servant of Aura is typing. Oh, okay. Alright, I'll move on to the next question then. Okay. This is probably one of my favorite questions I've ever come across in any practice exam ever. I believe it was a HSC practice paper, but this is such a beautiful question. It like just give it a try. Octagonal. Yeah, I got it right. Flatus. Yeah, it's negatively charged. Magnetic field is into the page. Electric field is downwards. I probably should have made that clear. Yeah. Let me make that clear right now. Okay. Do we have answers from anyone but Flatus? Johan, do you want to give it a try? Yeah. Give it a try. Up. The charged particle does go up, but it's not the final like it's not the final part. Like its end path. it does go up. You're on the right track of thinking. But when it's moving up, what is its interaction with the other fields? Yep, Flatus got it. Flatus got it like really quickly, actually, like within a few seconds. The CP, the charged particle. If you're new to the stream, CP stands for charged particle. It's just slang. Sideways one. Yeah, you're half right, half right. Yes, it's left. CP stands for charged particle. So let's work out why it's going to the right left when it's. So we have positive, negative electric plates, and the electric field is going downwards, but the CP is negative, so it will actually go upwards because it goes the opposite direction of the electric fields. So initially it goes upwards, but notice how there's also a magnetic field. So, and because the magnetic field needs the charged particle to be moving to accelerate it, once the charged particle actually starts moving from the electric field, that's when a force is applied on it, and we can find the direction of the force based on right-hand slap rule. So since we've got charged particle moving upwards, and we've got so okay, let's work it out. Okay, charged particle going upwards, we've got a magnetic field going into the page. Our palm is pointing to the left, right? So you would say that there's force to the left, but notice how the charged particle is negative. So it's actually the back of the palm that we're looking at for the direction of the force. So once it starts moving, there's a force to the right. And then once it has that force, since it's a constant force, we have a circular motion. So we have circular motion, but once it gets to this point where the force is going down, because the particle is constantly accelerated up by the electric field, the downwards and upwards motion cancel out, or at least we assume it to cancel out because we don't know any other information. So because it cancels out, there's no net force, so it's constant velocity. No, because all our slap rules are based on a positive charge moving. Flatus. No, the thumb is pointing up because that's where the charge is moving. The charged particle is moving up, right? No. There's no current flowing in the diagram. There's only electric field. And because remember there's force. There's also force on a current moving charged particle in a magnetic field that also uses the right hand slap rule. So that's the rule we're using, and it's the exact same, except if the particle is negative, that means the direction of force is the opposite way. So instead of the palm of our hand, it's the back of the hand because the charged particle is negative. So that's why there's force to the right. And since there's force to the right and there's constant force, the charged particle has a circular motion, and once the force is pointing down the same direction of the electric field, because the electric field accelerates the particle up, the forces cancel out, or at least we assume them to cancel out. So the charged particle achieves constant velocity because the forces have cancelled out. Does that make sense to everyone? Yeah, that's correct. Thumb is up, so charged particles move going up. Fingers are into the page because magnetic field is into the page. That's right. Right hand slap rule. But the direction of force is not the palm. The direction of force is the back of the hand. Yeah, because the charged particle is negative. Yeah. Does that make sense to everyone? Does anyone have any more questions with this specific question, or is it all good for everyone? Cool. I will move on to the next question then. Okay. This is another calculation one. Sorry about that. Right off the bat, what rule, what formula are we using? Let's start with that. Or Flatus, we don't have that. We're not that niche. We're not that niche. That's not a formula in our book. We have to actually make it ourselves. But you're right. Yeah, Flatus is right. So we will have a So we have a moving charged particle, and since it's moving, it's positive, the direction is our palm. So it's positive CP. So force is down based on right hand slap rule. So there's a force downwards. And because that force is at a right angle to our velocity, force is the force of the magnetic force is equal to the centripetal force. It's converted into centripetal force. So it equals QVB sine theta equals mv squared over r. And now we can simply just cancel out the v, and we will have our equation. We'll move it over here. So QB sine theta equals mv over r. Now we know Q, it's 6. We know B, which is 3. Sine theta is 90 since the magnetic field is straight into the page. So it's perpendicular to the motion of the particle, which is gonna be only in the plane of the page. So it doesn't go interact with the magnetic field in anything else besides 90 degrees. So sine theta is 1. We know the mass, which is 2 micrograms. Velocity is 2000 meters per second. And we are trying to find the radius. So we just rearrange. And R equals R equals 2 over 9. So it's 2 over 9 meters. So there will be a path where the radius is 2 over 9 meters. Does anyone have any questions with that? Micro 10 to the negative 6? Yeah, probably. Whoopsies. No, Flatus, it says microgram. Yeah, good spot. Good spot, yellow. Oh, 10 to the negative 9. Oh, yeah, okay. Yeah, that makes sense. Yeah, so for those on the recording, it's 10 to the negative 9 because SI units are kilograms. So micro is another 3 powers away from the standard SI unit. So if normally SI units is like grams, normally it's like meters, seconds, so I assumed it was grams, but because it's actually kilograms, we need to add another 3 powers, 3 orders of magnitude of removal. So micro isn't 10 to the negative 6, it's 10 to the negative 9. And the radius is 2.22 times 10 to the negative 7 meters. times 10 to the negative 7 meters. Yeah, does anyone have any questions with that? B over QB. Sorry, Flatus, where'd you get the 1.602? Charge of a particle. Oh, we have the charge. It's 6 coulombs. Yeah, no, you're all good. You're good. So, was that for an electron? Yeah, okay. Cool. Okay, I'll move on to the next question then. Okay. Have a crack at this. All the right hand grip rule warriors from earlier. Have a crack at this. Flatus, just say clockwise, or anti-clockwise. Anyone have any answers? We've got clockwise from yellow. Alright. Let's clockwise from Arctic Wolf as well. Alright, let's do it together. So we've got the solenoid here. I'll just draw it like that. And the magnet is going down. Okay, I can't draw on this. Okay, but with the right hand grip rules, we have the north end upwards. So thumbs up and then just drag it down. Now, the magnet falling down, it will have a south end flux. So it'll have flux facing up. It'll have an increase of flux going up throughout the solenoid. So because there's a change in flux, there'll be a current voltage induced in the solenoid, and from that a current, and from that a magnetic field. So we need to work out what direction the magnetic field induced in the solenoid is. So we have thumb up going up, and it's going down into the solenoid. We have upwards, increase of upwards flux. So the solenoid will have increase in downwards flux. There will be an induced downwards flux in the solenoid because that will oppose the upwards flux of the bar magnet. So because there's downwards flux in the solenoid, let's take a look at that with the right hand grip rule. We have thumb as the magnetic flux and the direction of magnetic flux slash magnetic field, and our right hand's fingers curls clockwise. So clockwise is correct. And with the south end, it's the same logic. So south end going down, there's a south flux, increase in south flux. Magnetic field was from north to south. Yeah. But with a bar magnet, because the north end is up on top and south end is on bottom, the magnetic field loops around. It goes up from the top, but it then loops around back to the bottom, and the magnetic field lines are pointing up towards the south because it flows from north to south, right? So because the south end is falling through the solenoid, there's an increase in flux where the field lines are pointing up. So because there's the increase in flux in the field lines pointing up, we need to find the induced flux in the solenoid will oppose that. So there's an increase in pointing up, so there would be an increase in pointing down with the solenoid. So the solenoid will have a magnetic field that points down, and down will mean that the north pole is on the bottom and the south pole is on the top. So north flows from north to south, and the magnetic field lines point down from the north. It flows up back into the south, and it points down to the south pole as well. Yeah. I appear to have some problem with the PowerPoint. I can't access it. So I'm just gonna close it and reopen it. Okay, it's not responding. So does anyone have any questions so far with electromagnetism? Anything we've talked about so far? Okay, on to the next question. I've got it back up. Did anyone have any questions with the previous question before we go and do the next question? No? Okay, let's move on to the next question. So this is a real question from QCAA in the multiple choice section. It was on the 2022 exam, paper 1. And I'm sure most of you might have seen this already, but for those who haven't, it's probably the most cooked question QCAA has ever written, especially for a multiple choice section. So, first thoughts, what are we doing with this? What formula, what rules, what are we doing? Yeah, you got this, Jonah. Or you, Jonah. What formula are we using? Where are we starting? Like, what formula are we using? Yellow, B equals mu naught Ni. Not quite. We have, so look at our values. We have number of turns, not turns per meter, mind you, number of turns. We have area. We have magnetic field strength, and we have a voltage. We have an EMF of 6 volts. So we have EMF of 6 volts. What does that suggest? Combined with the area, what does that suggest the formula we need to use is? Yeah, exactly. EMF equals negative N, the delta BA over delta T. So we'll use EMF equals negative N a cos theta. Remember, it's because the full flux equation includes the cos theta. And let's substitute everything in. So we have 6 equals negative 3,000. And we can ignore the negative because we're only dealing with the magnitudes. And the negative is only there for Lenz's law. So we'll only deal with the magnitudes. We know our magnetic field and our area is constant. So we have 2 milliteslas times 0.1 by 0.2. And this is times delta cos theta over delta T. So let's solve for everything, and let's just get the unknowns on one side. So if we do all the working out, we should get we should get delta cos theta over delta t is 50. Now, where do we go from here? Does anyone have any ideas? That's fair, Han. T equals 1. Okay, you've got good thinking. It's tricky here because we've got a ratio of two unknowns. Like, we don't know theta and we don't know t. We don't know the intervals of theta that it hits, and we don't know the intervals of time that it hits. However, we can look at the question to see what it wants us to find. It wants us to find revolutions per second, and the way we do that is that revs per second equals 1 over t for a single revolution. So let's find t for a single revolution. So t for a single revolution this will be when, if we have this as the coil, if we use this to represent the coil, when the coil has spun its quarters 4 times. So because a single revolution is the coil spinning and going through theta from 0 to 360, with cos theta it will go from 1 to 0 to -1 to 0 back to 1. But if we just go from 1 to 1 again, it's not really useful, right? So let's go from 1 to 0. So consider a quarter turn. And we're assuming that the rate of rotation is constant. So the time taken for a quarter turn will be a quarter of the time taken for a full turn. So for a quarter turn, cos theta will go from 1 and then go to 0. So the difference in cos theta will be 1. Or, well, -1, but we'll work with only magnitude. So we'll just say that it's 1. Now, delta time, we don't know. We don't know delta t. So let's go 1 over delta t equals 50. So 1 over 50 equals delta t. So that's for a quarter of a turn. So for a full turn, four times delta t equals 2 over 25. So delta t will be full turn. Let's say full t equals 2 over 25. Now, for the revolutions, that's 1 over t. And we know the time for a full revolution is 2 over 25. So 1 over 2 over 25, we get 25 over 2. Oh crap. We get 25 over 2, and you can take it from there. So the revolutions per second ends up being 25 over 2, and that simplifies to 12.5. But we want the minimum number of revolutions per second, and that usually is a whole number. So what they want is a whole number, and the closest whole number in the options is option C, which is 13. So the answer is option C. Does anyone have any questions with that? Yellow feels bad for future me who has to deal with this. Well, good thing you've already dealt with it. Yeah, but does anyone have any questions in general, like with just general electromagnetism? Not even specific questions, just general concepts or topics. Was this a question we learned? Yeah, this was the question you can use integration for to find area under the curve for the average for the average EMF, I believe. Oh, we got another one solving the sound. Yeah. The thing with the integration approach is that the answer you get at the end is in radians, so you have to radians per second, so you have to convert it into revolutions per second, which tripped me up several times. And overall, the integration approach is only like exclusive to method students. Uh, yeah. So, does anyone want me to go over any topics? All right, that's all good. That's all good, Yellow. I'm glad it was really helpful. Does anyone want me to go through the integration approach for this question then? Because Jonah mentioned it. I'm not too sure if I remember exactly how to do it. Yeah, with calculus. I believe it's to find the average EMF of 6V. No. This wasn't it wasn't a syllabus thing. It was an alternative approach to doing this question. Yeah. Okay. Yeah. Let me just. Okay, can you see that? You can't see that. Let me just screen share again. So we have with the calculus approach, it was relying on it used integration under the curve of cosine, because that was the thing we were changing with the magnetic flux, and we integrated the area, but we divided that area by 2 pi, or the interval we integrated with, to get the average voltage. And then once we found that, that meant we could find the angular velocity. So once we found the angular velocity, which was radians per second, then we convert that into revolutions per second. Okay. So we have average voltage equals 6, which equals so we have time here, and we have the voltage, and because it's using cosine, we have a sine graph with our voltage is a sine graph. So to find the average voltage, we'll take the interval from 0 to pi. The ink's not working. We can do that because it's periodic sine. So what we do for one part, we do for the other. It applies. What we do to one part applies to the whole function. Okay. It's just not working. That's great. Okay, I think I might need to restart PowerPoint again. Okay. Okay, PowerPoint's gone. Restarting it. So we have the alternative method. We have voltage, we have time, and voltage is the derivative of phi over dt, because phi is BA cos theta, and theta is changing with time. We have a sine wave, and we'll take interval, like I said, 0 to pi. So the average equals 6, which equals 1 over pi. Go integral of 0 to pi. We go BA sine, so NBA sine omega theta. No, sorry, omega t dt, since theta equals the angular velocity times the time, so it's omega t. This will go 6 equals 1 over pi times 3,000 times, was it 2 to the negative 3? Missing a negative. No, because the negative cos theta, it turns into because negative cos theta derives into positive sine theta, and also we're also considering magnitude anyway. Yeah, at negative n, no, because voltage is negative n d phi over dt. 1 over pi, because we're taking the area from 0 to pi. So 1 over pi minus 0 averages it. Yep. So 6 equals pi times 2 times 0.1 times 0.2, and then we integrate sine omega t, so we have times omega, and we have negative omega cos omega t from pi to 0. 6 equals, so 0.12 over pi times just absolute it, omega pi. Sorry. Because cos is omega t, the function should be sine omega NBA sine omega t. Because you're deriving it, so you multiply it. So so we have times omega, so omega over omega. Okay, so we have 6 pi over 0.12 equals cos I can't quite remember. The bounds would be modified by omega. So it'd be 0 to pi over omega. omega cos yeah, and so it's yeah, okay. Yeah, sorry about that. So we're integrating from 0 to pi over omega. So when we substitute into t, it's pi over omega, so it's just cos pi minus cos 0. So, and that is equal to that's 1, that's -1. That is equal to 2. So omega times -2, but we absolute it. Oh, there was a negative there anyway, so it's +2. So we have 3 pi over 0.12 equals omega. So 3 pi over 0.12. So omega equals, that results in 25 pi radians per second. And because we want revolutions per second, we divide by 2 pi. And that equals 25 over 2, which equals 12.5, which is about 13. Yep, that's the integral way to do it. Yeah, but this is really out of syllabus, because this was what me and Jonah's physics teacher thought the method was, but the actual method is the one where you just allocate a random interval for the coil to turn, and then you find the time taken for that. But if you have a more complex more complex turning or change in voltage, and they still want the average voltage, say it's a function like this, and they want the average voltage for that interval. So that's voltage and that's time. So average is 1 over a minus b, b minus a, and then integral ab ft dt. Oh, Flatus, have you seen my cooked physics question before? I don't think you have. Yeah, I just sent it. Yeah. But does anyone have any questions about electromag? Like anything to do with the topics, anything in the. No, that question wasn't in the masterclass, but I should have put it in the masterclass. You're right. Study tips for physics specifically. Yeah, I believe Jonah mentioned most of like the relevant physics study tips. In general, you are yellow. You're year 12. In general, I'd say for like a general course of the whole year, I reckon stay relatively chill with internals. Like, keep on top of your notes and all your understandings, but you don't have to stress about internals too much. Like, definitely put in effort to get like A plus and like get full marks, but you don't need to get like you don't need to stress too much about it um because your internals are assessments and they're much easier to get full marks in. Yeah, yeah, what Flatter said as well. Like with the motors and generators, like if your family has an electric car or like you drive an electric car, think about how your car actually accelerates. It's by force on a current carrying wire, and how the regenerative braking is. And yeah, if you're like washing your hands with soap, think about how that soap is actually a broken up triglyceride, and how the fatty acid chains form micelles with water and other non-polar substances. Yeah, yeah, that's chemistry. You don't need to worry about that. In yeah, in physics. Yeah, exactly what Jonah said. Oh, Jonah, you should try this question. Unless there's any other like general study questions or like electromagnetism questions, I might end the recording here. I'll stay in the VC, but just for the sake of the recording, don't so it doesn't get it doesn't get like it doesn't drag on for too long. Alright, I'll end the recording there. Yeah, no worries, no worries. It's it was, I was definitely hoping this was gonna be shorter, but at least it wasn't 4 hours like chemistry from last year with Ashan. But anyway, I'm gonna end the recording here. Uh, so that's the end. And I'll stay in